Bismillahirrahmanirrahim. So we'll solve problem 424 here. It says we have steam enters a well insulated horizontal nozzle. Nozzle is a device used generally to increase velocity by decreasing the cross-sectional area of the flow. So something like this, okay, where we have flow coming from here and leaving here. So we call this is 1, this is 2 at steady state. So this is steady state device, okay, and the steam enters with a velocity of 10 meters. So this is V1 equals 10 meters per second. If the specific enthalpy decreases by 45, decreases means that H1 minus H2 equals 45 kilojoule per kilogram. So it decreases. So H2 is less than H1. Determine the velocity of the exit. So V2 we need to find it. Now let's use the energy equation, right? So we are given H1 minus H2. There is nothing else here. We don't have pressure or anything. So we use the energy equation, which is Q dot minus W dot plus M dot. Since this is one inlet and one outlet, so we use this for H1 minus H2, inlet minus outlet, specific enthalpy, plus the change in the kinetic energy, inlet kinetic energy minus the outlet kinetic energy. And we are told here it's horizontal nozzle, so Z1 equals Z2, Z1 equals Z2, therefore no change in the potential energy. And we are told it's steady state, so dE dt is 0. We are told it's well insulated, which means that the heat transfer is 0. And nozzle is a device like this, so, and we don't have any work producing or providing device, no shaft work, no electrical work, so this is also 0. So we can divide by. Now we need to be very careful here. H1 minus H2 is in kilojoule per kilogram. So for the change in the kinetic energy, if we are going to use here kilojoule per kilogram, we need to divide by 1000, because V1 square minus V2 square over 2, this will give us only joule per kilogram. So to convert it into kilojoule, we need to divide by 1000. So here, divide by 2000. Yeah, half. So this is a very important thing that some students forget. So we already have H1 minus H2 given to be 45. So we can write V2 equals, we take it step by step, we take V2 on the other side, so this is 2000 equals V1 square 2000 plus H1 minus H2. So we multiply by 2000, we have V2 square equal V1 square plus 2000 H1 minus H2. And by that we can get V2. It's the square root of this. Okay, and this will be in meters per second. Okay. This is the another problem, and we are also dealing with nozzle. So here we have steam with P1. I changed the numbers because, as I told you, that this book has an issue with the numbers, that if you use the numbers given, then we'll need to do a lot of interpolation, and I don't want to waste time with that. So this here I will take it as 3. So we have nozzle. Let's draw that. This is 1, this is 2. So P1 equals 3 megapascal, and T1 equals, I change it into 360 degrees Celsius, enters converging diverging nozzle. Okay, so this is not just a nozzle, it's a converging diverging nozzle, which means that first it will converge, then it will diverge. I will tell you why or where this is used. So this is converging diverging nozzle operating at steady state. Okay, the velocity stream at the inlet is 8, so V1 equals 8 meters per second, and the velocity exit, so V2 600 meters per second, and P2 equals, again I change this into 1.5 megapascal. There's negligible heat transfer, so Q is 0. Neglect the effect of change in the potential energy. Okay, so change in potential energy is 0. Determine the exit area of the nozzle. So we need what is A2. And we have the mass flow rate is 2.5 kilogram per second, which will be the same at the inlet and the outlet, because this is state, okay, and one inlet and one outlet. So first I will tell you where this converging diverging nozzle used. You will take this more in fluid mechanics, but for converging nozzle, okay, for compressible flow, the maximum velocity that can be reached here at the outlet is velocity of the sound velocity. Okay, velocity of sound, V max equal V sound. If we need, so, and this is called Mach number of 1, Mach number, where Mach number equal velocity divided by C, where C is the velocity of sound. So when Mach number at the exit equal to 1, that's the maximum velocity. If you want to increase velocity more, then we need to use divergent nozzle, because then to increase velocity we need to increase area. This is only if we have compressible flow. Okay, this feature for compressible flow, and you notice here that the velocity, is 600 meters per second. 600 meters per second is greater than velocity of sound. Okay, so this can be only reached if we have converging diverging nozzle. Okay. You can read this more in your own time. So now we need the area to find that. We need to apply the energy equation. So let's see what the energy equation can give us, because here in this state we have two properties, P1 and T1. In the exit we have only one property. We need another property to find what is the specific volume, because if we have the specific volume, then we can say, okay, m dot equal A to V2 over the specific volume 2. Okay, we have velocity V2 here. Okay, velocity at the exit, we have it. If we can find V2 from the table, then we can find A2. So we need to find this. So we need to find another property at the exit, and that we can find it if we use the energy equation. So let's see the energy equation. Q dot minus W dot plus M dot H1 minus H2 plus V1 square minus V2 square over 2000. Okay, don't remember here divide by 1000 because these H will be in kilojoule. So here we are told enters negligible heat transfer, so Q dot equal to 0. And in nozzles, generally we don't have work. And we have steady state, so this is dE dt equal to 0. Then we can lose 100. From here, we can find from P1 and T1, we can find H1. We'll see now how. Then H2 equals, so we take H2 to the right hand side, H1 plus V1 square minus V2 square over 2000. Now we have V1 equal 8 meter per second, we have V2 equal 600 meter per second, so we put them here, divide by 2000. We need H1, so we have pressure of 3 megapascal, temperature of 360. So we go to table A3, for example. We can go to table A2 also. If you go to A3, 3 megapascal is 30 bar. And we see here the T set is 233. Our temperature is 360, which is greater than 233.9. Therefore, we are in superheated region, vapor. Okay? You see here that using tables is very important. So we go to the superheated with 3 megapascal table and 360. So you see here why I selected these, because they are readily available. Here, this is V, this is U, this is H. So this is the value of H, of the enthalpy. H1, 3138.7. So H1 equals 3138.7 kilojoule per kilogram. So we can find this. So we have 3138.7 plus 8 square minus 600 square divided by 2000. And this will equal 2958.7 kilojoule per kilogram. So now for point 2 we have H2 and P2. So now P2 equal 1.5 megapascal. 1.5 megapascal, we can go to the table again, the superheated table. We see where to find this. So let's go to the saturated table, looking for these two values, 1.5 megapascal and the pressure. So this is table A3. 1.5 megapascal is 15 bar. So for that pressure, we look at Hg and Hf. This is Hg and this is Hf. Our value is H equals 2958.7 kilojoule per kilogram. Our value, you see, it is greater than Hg. Therefore, we are in superheated vapor region because H is greater than Hg. Okay, so we go to the superheated with table of 1.5 bar temperature, and we look for H, the value of H equals 2958.7. So here we look 2958, it will be between these two values, 2899 and 299. We need the specific volume, which is this one. So here we have H2, which is this value, and here we have V2, so we use interpolation. Here we'll have to use interpolation to find V2. Once we have V2, okay, from these two values, so we found V2, then we take this value here, and then from this relation we have A2 equals m dot times V2, which we found, divided by the velocity at the exit, and that will give us the area. Thank you.